January 1943. Eastern Front, Soviet Union. The vast, frozen expanse of the Eastern Front was a brutal canvas for war. Below, the titanic clash of armies ground on amidst snow and ice. Above, in the unforgiving winter sky, the Luftwaffe's Messerschmitt Bf 109 fighters and Focke-Wulf FW-190s battled the Soviet Air Force. But the Germans were fighting another enemy, an unseen adversary that was costing them precious aircraft and skilled pilots: the cold. Hauptmann Klaus Richter, a veteran Bf 109 pilot, cursed as his hands, even gloved, stiffened around the controls. His fighter, typically a nimble hunter, felt sluggish, protesting against the biting temperatures that often plunged to minus 30 degrees Celsius and below. He had just survived a brutal dogfight over the frozen steppes, his Messerschmitt riddled with bullet holes. But he knew the hardest part of his mission was yet to come: the landing. "Landing gear down, Klaus," crackled the voice of his wingman, Lieutenant Schmidt, over the radio. Richter responded with a grunt. He pushed the lever for the landing gear. Nothing. He pushed again, harder. A faint, strained whine emanated from beneath the cockpit, but the familiar thud and shudder of the undercarriage locking into place never came. Below him, the makeshift, snow-covered airfield near Stalingrad loomed. A red flare shot up, a warning. His landing gear was stuck. This wasn't an isolated incident. Across the Eastern Front, German pilots were reporting an alarming, inexplicable surge in landing gear failures, especially after prolonged flights in extreme cold. Fighters would return from missions, their engines still roaring, only to belly land or crash land on their makeshift airfields, often bursting into flames. It was a fatal mistake that was draining the Luftwaffe of vital resources, not through enemy action, but through mechanical self-sabotage. The German High Command blamed the rough airfields, the hurried maintenance, the exhaustion of the pilots. But Richter knew better. He had felt it in the unresponsive controls, the sluggish flaps, the delayed deployment of his landing gear. It felt like his aircraft was fighting him, not just the Soviets. Richter tried again, pumping the lever with desperate force. His hydraulic pressure gauge flickered ominously low. The whine below became a tortured squeal. The undercarriage was simply refusing to extend. "I have no gear, Schmidt." "Repeat, no gear." Richter's voice was tight with grim realization. He was going to crash. Meanwhile, hundreds of miles away, in a dimly lit, cold RAF laboratory at Farnborough, England, Dr. Eleanor Vance, a brilliant British organic chemist, was examining a small, dark vial of captured German hydraulic fluid. Her lab coat was splattered with various chemicals, her brow furrowed in concentration. The vial had been recovered from a crashed Focke-Wulf FW-190 on the Western Front, where winter temperatures were harsh, though not as extreme as the Eastern Front. Initial reports from Allied mechanics noted that the German hydraulic systems seemed sluggish in the cold. "This is not standard stuff, Dr. Vance," remarked Wing Commander Alastair Finch, our composite engineering hero, now specializing in chemical analysis, looking over her shoulder. "Our intelligence suggests the Germans are having severe issues with their landing gear and flaps, especially in the east." Dr. Vance, however, had already noted something peculiar. She had subjected the fluid to extreme cold in a makeshift freezer. When she pulled it out, it was no longer a free-flowing liquid. It had become thick, almost gelatinous. "It's the viscosity, Alastair," Vance announced, holding the vial up to the light. "At normal operating temperatures, it's perfectly fine. But when exposed to severe cold, it transforms. It becomes like treacle, like frozen honey." The implications were stark. German aircraft, designed for advanced hydraulic systems, were being effectively crippled by the very fluid meant to power them. The fatal mistake wasn't in the design of the hydraulics, but in the chemistry of the fluid itself. Germany, facing wartime shortages of critical petroleum additives, was using a substitute hydraulic fluid that performed catastrophically in extreme cold. This was the unseen enemy, the frozen sky, that was grounding the Luftwaffe's best fighters, not through enemy bullets, but through the insidious chemistry of compromised wartime materials. January 1943. RAF Chemical Laboratory, Farnborough, England. Dr. Eleanor Vance worked tirelessly, analyzing the samples of captured German hydraulic fluid. Her lab, usually a place of quiet, methodical research, now buzzed with a sense of urgency. Wing Commander Alastair Finch watched her, understanding the profound implications of her discovery. At typical engine temperatures, say around 60 degrees Celsius, Vance explained, demonstrating with a rheometer, this fluid flows almost identically to our own. But as the temperature drops below freezing, rapidly approaching minus 10 degrees Celsius, then minus 20 degrees Celsius, its viscosity skyrockets. It becomes incredibly thick, almost resisting movement. She showed Finch graphs illustrating the exponential increase in viscosity. Below minus 25 degrees Celsius, it's essentially a jelly. No pump, no matter how powerful, can force it through narrow hydraulic lines and delicate valve mechanisms with the required speed and pressure. This was the treacle trap, the insidious chemical flaw that was turning the Luftwaffe's technologically advanced hydraulic systems into frozen, unworkable messes. The hydraulic fluid, a seemingly minor component, was proving to be a massive, fatal mistake for German air superiority. Finch understood the engineering implications immediately. Modern combat aircraft, like the Bf-109 and Fw-190, relied heavily on hydraulics for critical functions. Landing gear, extension and retraction. Flaps, essential for controlled takeoffs and landings, especially on short, rough airfields. Ailerons and rudder, power-assisted for precise control at high speeds. If the hydraulic fluid became too viscous, these systems would respond slowly, erratically, or not at all. A pilot, desperate to lower his landing gear after a dogfight, would find the controls unresponsive, his flaps refusing to deploy, turning a routine landing into a guaranteed crash. Finch dispatched urgent communications to Allied air forces, particularly the Soviets, whose pilots were operating in the same brutal conditions. The intelligence was simple. German aircraft would exhibit critical hydraulic failures in extreme cold, especially after sustained high-altitude flight followed by descent for landing. This knowledge introduced a new, unseen dimension to the air war. Allied pilots now understood that their German counterparts weren't just battling them. They were battling their own aircraft's faulty chemistry. Back on the Eastern Front, Hauptmann Klaus Richter braced for impact. He fought his unresponsive Bf-109, trying to guide it onto the snowy runway without landing gear. The ground rushed up. The last thing he saw before the crunch of tearing metal and the flash of sparks was the thick, sluggish movement of his hydraulic pressure needle, stuck in the dangerously low zone. The crash was a brutal, bone-jarring event. The Messerschmitt slammed onto the snowy runway, skidding for 100 yards in a shower of sparks and tearing metal, its cockpit shielded only by luck and its heavy engine block. Rescuers pulled Richter from the wreckage, alive but battered and concussed. German ground crews rushed to the site, expecting to find the usual cause: enemy shrapnel or pilot exhaustion. They meticulously inspected the wreckage, finding no bullet holes in the main hydraulic lines. The lines were intact, the pumps undamaged. Yet, the hydraulic fluid, when tested in the cold, was thick, resistant, and nearly immobile. Richter, recovering in the field hospital, insisted to the examining officer, "It wasn't me. The gear wouldn't come down. The fluid was frozen. I tell you." His complaints were noted, then quietly dismissed. The official report, influenced by the fierce pride of the Luftwaffe and the fear of admitting a systemic flaw, simply cited pilot error during landing approach and loss of control due to exhaustion. The costly, invisible enemy, the thickening, freezing chemistry flowing through the Bf-109's veins, remained officially unacknowledged by the Luftwaffe High Command. The treacle trap had claimed another victim, silently costing the Luftwaffe a pilot and a vital fighter, not through combat, but through the official blindness of a leadership unwilling to concede a fundamental chemical flaw. The stage was set for the Cold War in the cockpit to continue. February 1943. Luftwaffe Airfield, Eastern Front. Hauptmann Klaus Richter miraculously survived his crash landing, albeit with a broken arm and severe concussion. His Bf-109, however, was a write-off, twisted metal, a shattered engine, and a hydraulic system that, once inspected, revealed no obvious external damage. The internal culprit, the treacle trap, remained an invisible killer, a Cold War in the cockpit that the Luftwaffe refused to acknowledge. German engineers and maintenance crews, under immense pressure, meticulously examined the wreckage. Their reports consistently blamed rough landings, pilot error, battle damage, or poor field maintenance. The idea that a fundamental chemical flaw in their hydraulic fluid could be causing such widespread and costly failures was too unthinkable, too damaging to the narrative of German technological superiority. This was a critical, fatal mistake, a blindness born of pride and wartime exigency. Richter, recovering in a field hospital, tried to explain, "It wasn't me. The gear wouldn't come down. The controls were heavy, like moving through mud." His complaints were noted, then often attributed to shock or the trauma of the crash. The Luftwaffe High Command continued to demand more sorties, more aggression, dismissing the rising accident rates as an unavoidable consequence of fighting in the brutal Russian winter. They knew of some cold weather performance issues with their hydraulic fluid, but believed them to be minor, manageable. They simply did not grasp the catastrophic extent of the problem. Meanwhile, at RAF Fighter Command Headquarters, UK, Wing Commander Alastair Finch presented Dr. Eleanor Vance's findings to a gathering of senior RAF officers and intelligence analysts. Maps of the Eastern Front were spread out, marked with newly correlated German aircraft losses attributed to landing incidents. Dr. Vance's analysis confirms our theory, Finch stated, pointing to a graph showing the plummeting efficiency of German hydraulic fluid in sub-zero temperatures. Their hydraulic systems, designed for speed and precision, are literally seizing up in the cold. It's a systemic vulnerability, not a series of isolated incidents. The intelligence was immediately shared with Soviet liaison officers for the VVS, Soviet Air Force, who had been suffering similar, though less pronounced, issues due to their own wartime material compromises. This was invaluable information. It shifted their understanding of the air war. This is not just about avoiding combat. Gentlemen, Finch continued, this is about how we fight them. Force them higher. Keep them in the extreme cold for longer. Prolong the engagement. Let the elements and their own chemistry defeat them. New tactical directives were issued to Allied fighter squadrons operating in cold climates. High-altitude engagements. Whenever possible, lured German fighters to high altitudes, above 20,000 feet, where temperatures were most extreme. Prolonged combat. Instead of quick, decisive passes, engage in longer, more maneuverable dogfights to keep the German aircraft exposed to the cold for extended periods. Targeting damaged aircraft. Prioritize German aircraft showing any signs of hydraulic sluggishness, slow flap deployment, erratic control surfaces, knowing they were already compromised. This knowledge introduced a new, unseen dimension to the air war. Allied pilots now understood that their German counterparts weren't just battling them. They were battling their own aircraft's faulty chemistry. The enemy wasn't just in the cockpit across from them, but also flowing through their hydraulic lines. Back on the Eastern Front, Lieutenant Schmidt, Klaus Richter's wingman, took off in his FW-190. He knew Richter's crash had been officially labeled pilot error, but he also knew his friend. He'd felt the heavy controls himself. The air was bitterly cold. As he gained altitude, Schmidt could feel a subtle stiffness creeping into the aileron controls, a slight delay in the flap response during his pre-landing checks. It was a terrifying, nagging feeling, the Cold War in the cockpit. He was flying a marvel of German engineering, but in the depths of winter, it felt like a trap, its critical systems powered by a substance that betrayed him in the unforgiving cold, making every landing a roll of the dice. He, and many like him, were unknowingly flying compromised machines, caught in a fatal mistake that was rapidly turning their technological advantage into a deadly vulnerability. March 1943. Luftwaffe Medical Report, Eastern Front. The German High Command was baffled. Despite consistent combat victories reported by their ace pilots, the rate of operational aircraft losses on the Eastern Front remained stubbornly high. Moreover, the number of pilots suffering stress-related trauma or nervous exhaustion after non-combat incidents was climbing. This was the unseen attrition, a slow, insidious bleed of resources and manpower, directly attributable to the faulty hydraulic fluid, yet completely unacknowledged as a systemic fatal mistake. Medical officers reported pilots exhibiting severe anxiety before landing, increased rates of alcohol consumption, and persistent complaints of heavy controls or sticky gear. These were dismissed as symptoms of the brutal winter campaign and intense combat, rather than direct indicators of aircraft unreliability. The true cause, the compromised chemistry, remained a dark secret hidden within the very veins of their fighters. Hauptmann Klaus Richter, now partially recovered but grounded indefinitely, tried to put words to the invisible terror. "It's the fear of the return, her doctor," he explained to a bewildered military psychologist. "You survive the Soviets, you survive the flak. Then your own machine betrays you. You push the lever, but it does nothing. You are helpless. The ground comes fast." This psychological toll was immense. Pilots, instead of focusing solely on the enemy, were forced to battle their own aircraft's unpredictability. Every landing became a high-stakes gamble against an unseen foe, the thickening hydraulic fluid. Meanwhile, at RAF Liaison Office, Moscow, Wing Commander Alistair Finch reviewed the latest intelligence from the Eastern Front with Soviet Air Force Marshal Vasily Kuznetsov, a composite character representing a senior VVS officer. The VVS had enthusiastically embraced Finch's intelligence. "Our pilots now know, Tovarish Finch," Kuznetsov declared, tapping a map of the front lines. "When we see a Messerschmitt fighting sluggishly, or if we force him to a high altitude for a long time, we know his weakness. The cold is our ally." Soviet tactics had adapted. Instead of short, sharp engagements, VVS fighters, particularly the nimble Yak-9s and La-5s, would draw German aircraft into extended chases at extreme altitudes. They would use hit-and-run tactics, forcing German pilots to constantly operate their power-assisted controls, taxing the cold, sluggish hydraulic fluid. "They're using their flaps erratically," Alistair reported an RAF pilot seconded to the VVS. "You can see it. They try to outturn you, but their flaps won't respond fast enough. Then when they try to land, they're often belly up." This adaptation was proving devastatingly effective. German aircraft, already stressed by combat, were finishing missions with hydraulic systems pushed to their absolute limit. The unseen attrition was accelerating. German maintenance logs, later captured by the Allies, would reveal a shocking truth: a disproportionately high number of damaged in landing incidents, frequent reports of heavy controls, or sluggish response in hydraulic systems. An alarming increase in non-combat write-offs directly correlated with prolonged cold weather. The Luftwaffe, blind to the true systemic cause, continued to churn out more aircraft and train more pilots, throwing resources into a gaping wound. They believed they were fighting a war of attrition against the Soviets and the elements, unaware that a significant portion of their losses was self-inflicted, a fatal mistake born of compromised chemistry. Finch understood that the impact went beyond mere numbers. Every crash fighter was not just a loss of steel and aluminium. It was a loss of invaluable pilot experience, a drain on morale, and a significant diversion of precious manpower for recovery and repair. The unseen attrition was slowly, silently, but relentlessly corroding the very operational capacity of the Luftwaffe on the Eastern Front, turning their technological prowess into a hidden vulnerability, a chemical Achilles heel that the bitter Russian winter was relentlessly exploiting. April 1943. Luftwaffe Forward Command, Central Sector, Eastern Front. General Feldmarschall Wolfram von Richthofen, commanding the German 4th Air Fleet, paced his frigid bunker. The spring thaws were beginning, but the operational reports from his fighter squadrons remained grim. Despite the receding cold, the pattern of landing incidents and hydraulic issues persisted, albeit with less severity than the peak winter months. This was strategic paralysis, the insidious outcome of a systemic fatal mistake that was draining the Luftwaffe's offensive capacity. "Our operational readiness is plummeting," General Feldmarschall reported his Chief of Staff, Oberst Erich von Manstein. "Pilots are exhausted. Aircraft are being written off faster than replacements can arrive. The Soviets are growing bolder in the air." The root cause, the compromised hydraulic fluid, remained largely misunderstood or dismissed within the German High Command. They attributed the problems to a myriad of smaller issues: worn parts, stressed airframes from combat, battle damage, or even the ubiquitous pilot error. The true, systemic fatal mistake, the chemical vulnerability, was simply too inconvenient, too damning, and too fundamental to the entire supply chain to be openly acknowledged. The consequence was a crippling reduction in the Luftwaffe's ability to support the ground forces, which were already reeling from the winter campaigns. Critical missions, such as close air support for besieged strongpoints or fighter escort for bomber formations, were often curtailed or canceled due to a lack of serviceable aircraft. Meanwhile, at RAF Combined Intelligence Center, London, Wing Commander Alastair Finch and Dr. Eleanor Vance continued to analyze captured German components and intelligence. The full picture of the strategic paralysis was now terrifyingly clear to the Allies. "Their entire air doctrine is being undermined," Alastair Vance explained, pointing to a diagram of a Bf-109's hydraulic schematic. "They designed these aircraft for rapid deployment, quick turnaround, and aggressive fluid combat. But if their flaps won't deploy reliably, if their landing gear fails, if their gun feeds jam, they can't do any of that." The intelligence was shared widely. Allied air forces now understood that the German air arm was suffering from a deep-seated, self-inflicted wound. It wasn't just about destroying aircraft in the air. It was about the cumulative effect of hundreds of non-combat losses on the ground, wearing down the Luftwaffe from within. The fatal mistake of prioritizing production volume and using compromised chemical components had ripple effects across the entire German war machine. Reduced sortie rates, fewer available aircraft meant fewer missions flown. Loss of experienced pilots. Crashes consumed invaluable combat veterans. Diversion of resources. Manpower and materials were constantly siphoned off to repair or replace crashed aircraft. Psychological impact. Pilots' confidence in their machines eroded, leading to hesitation and reduced combat effectiveness. This strategic paralysis meant that even when the Luftwaffe did have an advantage, they struggled to capitalize on it. Their technologically advanced fighters were often grounded, undergoing repairs, or were lost to preventable accidents, making them less reliable than even some older Allied designs. Back on the Eastern Front, General Feldmarschall von Richthofen received yet another report for Bf-109s from a single squadron lost in landing incidents over the past week with no enemy contact. He slammed his fist on the table. "This cannot continue. We are losing the air war on our own airfields." The irony was brutal. The Luftwaffe, designed to be the spearhead of the Blitzkrieg, was being blunted not by superior enemy numbers, though those were growing, but by a silent, chemical enemy flowing through the very lifelines of its aircraft. The strategic paralysis was a testament to how deeply a seemingly minor material compromise could penetrate and cripple an entire fighting force, turning an engineering marvel into a victim of its own hidden chemical flaw. June 1943. Luftwaffe Research and Development Center, Rechlin, Germany. Dr. Heinrich Brandt, a brilliant but increasingly gaunt German chemist responsible for hydraulic fluid development, stared at a viscosity test report. His brow was furrowed with a mix of frustration and despair. The numbers confirmed what he had known for months, what he had warned about repeatedly in censored reports. The hydraulic fluid designated RS-200, was dangerously inadequate for extreme cold. This was the work of the architect of deficiency, the desperate, compromising nature of Germany's wartime economy, embodied in a vial of liquid. Brandt had argued for better additives, for more rigorous testing, for a reduction in production quotas to ensure quality. But his pleas were met with the harsh realities of wartime shortages. "We simply don't have the petroleum derivatives," Dr. Brandt, his superiors had told him repeatedly. "The Eastern Front needs fluid now, not perfection. Produce, produce, produce." This was the fatal mistake at its core. The political and economic imperative for volume overriding critical engineering and chemical integrity. The Luftwaffe High Command, driven by Hitler's demands for endless campaigns, had unwittingly signed off on the systematic self-destruction of its own air assets in cold climates. They had chosen quantity over quality, sacrificing reliability at the altar of production targets. Meanwhile, at RAF Technical Intelligence Unit, Farnborough, Wing Commander Alistair Finch and Dr. Eleanor Vance were preparing a comprehensive report on German hydraulic fluid for distribution to all Allied air forces. Their findings were now irrefutable. "It's not just the viscosity, Alistair," Vance explained, pointing to detailed chemical diagrams. "We found evidence of accelerated wear in the pump seals and valves in the fluid's residue. The lower quality base oils and lack of proper lubrication enhancers are also contributing to premature mechanical failure." This meant the problem wasn't just temporary cold-induced sluggishness. It was causing permanent damage to the hydraulic systems themselves, leading to a cascade of maintenance issues even in warmer weather. The fatal mistake was compounded by the long-term wear and tear it inflicted. The report detailed not only the chemical composition of RS-200, but also recommended specific Allied tactics to exploit this weakness. Sustained high-G maneuvers forced German fighters into prolonged, tight turns to rapidly cycle their hydraulic systems, exacerbating fluid performance issues. Targeting landing phases, focused ground fire, or opportunist attacks on German airfields during known landing times, knowing aircraft were most vulnerable to hydraulic failure then. Psychological warfare. Disseminate leaflets to German troops hinting at the unreliability of their own equipment, further eroding morale. The architect of deficiency had created a systemic vulnerability that Finch and Vance had meticulously unraveled, turning a chemical weakness into a potent strategic advantage for the Allies. The German Luftwaffe, once the symbol of cutting-edge technology, was increasingly operating compromised machines, a hidden flaw eroding its fighting spirit from within. Back in Germany, Dr. Brandt received another report, a sharp increase in hydraulic pump failures in Bf-109s on the southern front, where temperatures were moderate. The problem wasn't just the cold anymore. The inferior fluid was simply breaking down the entire system prematurely. He knew his warnings had gone unheeded, his science overruled by necessity. The Luftwaffe's fatal mistake was not just a single design flaw or a tactical misstep. It was a deeply ingrained systemic vulnerability, born from the pressure cooker of wartime resource allocation and the relentless pursuit of production above all else. The architect of deficiency had built an air force that, for all its might, carried within its very veins the seeds of its own destruction. A chemical Achilles heel that the Allied intelligence had now fully exposed and was actively exploiting. The fluid that powered the German war machine was also poisoning it, making every mission a gamble against chemistry. Post-war, 1950s onwards, the roar of Merlin and Junkers engines faded into history, and the skies over Europe grew peaceful. But the bitter lessons learned from the Luftwaffe's hydraulic fluid crisis left an indelible imprint on aerospace engineering, fluid dynamics, and military logistics for decades to come. The case of RS-200, the German hydraulic fluid that turned into treacle in the cold, became a canonical case study, taught in engineering schools and military academies worldwide. It served as a stark, enduring example of how even a seemingly minor material compromise, driven by wartime necessity, could lead to catastrophic operational unreliability and significantly impact the course of a major conflict. Dr. Eleanor Vance, now a highly respected professor of chemical engineering, often presented the RS-200 saga in her lectures. She emphasized that the fatal mistake was not a singular design flaw, but a complex interplay of ambitious technology, severe material shortages, and a strategic blind spot within the German high command that prioritized production volume over critical component integrity. The Germans had brilliant engineers, Vance would explain, pointing to detailed chemical diagrams. But their ambition, fueled by Hitler's demands, outstripped their chemical and material resource base. They focused on engine power and airframe speed, but overlooked the fluid that made the entire system work reliably. Her lectures highlighted the primacy of fluid chemistry. High-performance hydraulic systems absolutely demand precisely formulated fluids capable of maintaining stable viscosity across extreme temperature ranges. German failures underscored the critical need for advanced chemical additives. The crucial role of materials science. Wartime shortages of specific petroleum derivatives forced Germany into compromises that created a systemic vulnerability. This showed how deeply chemical integrity influences mechanical reliability. The cost of unacknowledged weakness. The German High Command's refusal to acknowledge the systemic nature of the problem, instead blaming pilots or maintenance, prevented them from addressing the core issue, leading to unseen attrition and strategic paralysis. The legacy of the Luftwaffe's hydraulic fluid troubles profoundly influenced the design of subsequent generations of military aircraft. Post-war aerospace engineering placed an even greater emphasis on robust fluid systems, rigorous cold weather testing, and diversified supply chains for critical chemical components. The aim was to ensure that no air force would again be crippled from within by the very fluid meant to power its most vital controls. For surviving German engineers, like Dr. Heinrich Brandt, our composite character, the post-war years brought a bitter understanding. They had known the problems, had seen the frustration in the field, but were powerless to challenge the prevailing dogma of German engineering superiority and the overwhelming demands of war production. Only in retrospect, with Vance's comprehensive analysis, did the full, tragic picture emerge. We built birds of prey, Brandt reflected in a post-war interview, but we gave them frozen blood. They were magnificent, but in the cold, they became brittle. Our greatest strength, our speed and precision, became our hidden weakness, betrayed by a mere liquid. The story of RS-200 is a powerful testament to the often invisible battle of logistics, resources, and chemical integrity that underpins any military conflict. It showcases how meticulous scientific investigation, even into the smallest details of enemy material, can uncover vulnerabilities that contribute significantly to the broader strategic outcome. The advanced fighters of the Luftwaffe, once feared for their agility, ultimately faltered not just from Allied bullets, but from the corrosive, fatal mistake of their own compromised, cold-sensitive chemistry. Their failure left a lasting imprint, teaching future generations that true air power is built not just on speed and firepower, but on uncompromising, fundamental chemical reliability. This brings us to a final, thought-provoking question for our audience. Beyond hydraulic fluids, can you think of other historical or even modern examples where a seemingly minor chemical component or material, like a lubricant, a sealant, or a fuel additive, became the Achilles heel for a complex, advanced piece of military technology, leading to unexpected failures? Share your thoughts and insights in the comments below. I read every single one.